Good morning, everyone. So, keeping this long-standing tradition that we started yesterday, the last speaker is the chairman who makes for the next talk. Let me introduce our first speaker this morning, José Luis Cisneros from UNAM in Mexico. He's going to talk about joint work with Agustin and José Antonio Singer about secondary characteristic classes for normal surface singularities. And I guess the next lecture will be a continuation.
Yes.
Okay. So please, José Luis.
Thank you very much, Pepe. I thank you for the opportunity to give the talk here for this nice conference and meeting friends again. So we'll talk about this work we have been doing with Agustin and Jose Antonio, applying secondary characteristic classes to say things about singularities. So the talk is divided into these 5 sections. I will speak about characteristic classes of representations. Then I will talk about the Atiyah, Patodi and Singer Index Theorem for flat bundles, about construction of some elements in algebraic theory. Then I go to singularities and one application. Okay, so characteristic classes of representations. Well, we have a topological group when we have the classified space and the universal principal G bundle, and well, these are unique up to homotopy, and any principal G bundle over our compact space is classified, has a classified map, and we have a one-to-one correspondence between principal G bundles over X and homotopy classes of maps from X to the classified space. This, what we know, this construction is commutatorial in the group. And if we take the group with a discrete topology, this classified space is an Eilenberg-MacLane space of type KG1. And if we take the identity map here with a discrete topology and here the topological group, we take a principal G bundle over X, and if the classified map factorizes through the classified space of the group with the discrete topology, we say that the principal G bundle is flat, and the consequence is that any associated vector bundle of this principal bundle has a flat connection. So
how do you define flat connection if you're working not on a manifold, or X is for you always a manifold?
Well, it will be a manifold, but here just well, by definition, but there is yeah, you are right.
For me, it does not make sense to speak of a connection
yes,
if I'm not on a manifold.
This line makes sense if X is on the so principal flat principal G bundles correspond now to these homotopy classes, and if X is a compact space and we have vector bundles, then vector bundles correspond to homotopy classes again from the space to this classified space of GLM, and what here again it should be manifold flat vector bundles. They correspond to again homotopy classes of maps, but it also corresponds to representations of the fundamental group.
This works for any group, so this that you can rephrase this as representations of phi1 to G discrete. Or is it specific to GLM?
Well, here since I'm thinking in vector bundles, like
but if you take G principal bundles in the language, flat ones should correspond to representation of phi1 to G.
This Eilenberg-MacLane space.
Yes.
From this slide before.
Yeah. Okay.
So then we have this correspondence between the principal for flat bundles and representations. So I take now a compact manifold, a representation of the fundamental group, and there is the corresponding flat vector bundle. Okay, we say that the representation is topologically trivial if the vector bundle is trivial, it's topologically trivial. And we define, well, Atiyah did the Cheeger-Chern class of the representation as the Cheeger-Chern class of the flat vector bundle, the class here. And also we have that the first Cheeger class of the representation is the same as the first Cheeger class of the determinant, the representation. It will be useful later. And now secondary characteristic classes. Again, we have our manifold, our representation, and Chern by theory, using the curvature of the connection, using the curvature of a connection, constructs the Chern class. It's using some invariant polynomial, and you have a form, and if the vector bundle is flat, the connection has curvature 0, then this class is 0, and taking the exact sequence corresponding to this short exact sequence of coefficients, we have the long exact sequence. So it's like this: we have the Chern class, we have here the Chern class, which in our case for flat connection is 0. So that means that we have a pre-image. This is in the image. So Cheeger and Simons constructed a canonical pre-image using these groups of the differential characters. No, I won't go into details, but they construct a canonical pre-image of the Chern class, which is called the Cheeger-Chern-Simons class of this bundle, and we say that the Cheeger-Chern-Simons class of the representation is the corresponding class of the corresponding bundle. And then, we go to the oriented compact tree manifolds, not dimension tree. So we have our representation by the universal coefficient theorem, and since this Simons set is divisible, we have this isomorphism between the homology and homomorphism from homology to Simons set. So we can think of these Cheeger-Chern-Simons classes as homomorphisms, and if we take a class in H1 or the fundamental class of the manifold in H3, we define the Cheeger-Chern-Simons numbers, or CCS numbers for short, with respect to the corresponding homology classes, just evaluating them in the corresponding homology class.
Can I ask a question?
Yes.
So here you're focusing now on Chern classes and the group GLN. And I don't know in which generality Cheeger-Simons developed. So does their machinery work also for other groups? Let's, for example, say you would have the symplectic group or something? Or?
I think they will be more generous. Okay, so we have, in our case, we have just two CCS numbers, the first and the second one. Here, this is just enough to take the fundamental class. Any other class here is just a multiple. Here depends of the first homology group. We can have several generators. Okay, so how to compute these numbers? In the case when, I change now the name of the notation of the manifold to L because it will be a link. If the manifold is a rational homology tree sphere, how we compute this? Well, we have for this particular case, rational homology spheres, we have, within, I don't know, like this, the dual representation. Again, we take the determinant, and we have these three properties. The representation is topologically trivial if and only if the first Chern class is 0, or if the first Cheeger-Chern-Simons class is 0. This representation, the representation direct sum with the determinant of the dual representation is topologically trivial, and the first Cheeger-Chern-Simons class of the representation is the same as the first Cheeger-Chern-Simons class of the determinant of the representation. And there is a formula to compute this, the first one. So since GL1C is abelian, the determinant factorizes to the abelianization. So you have a representation, it factorizes like this. I will denote it by the determinant rho R.
Can you one page back? So,
yeah.
So what is coming in that you need the assumption of rational homology?
Because I will have some isomorphisms again in the similar to this with cohomology and homology. And in order to have, for instance, so you don't have this in general.
Okay.
No. The data in this case, these two classes correspond under an isomorphism. In the general case, yes.
Condition is needed.
Okay, so this a formula which is in a paper by DuPont. So you have you take a class in H1, which is the abelianization of the fundamental group of the manifold, and the first CS number with respect to this class is, as I said, the same as the determinant of the representation, and is given by this logarithm. Okay. So, well, this is a easy formula to compute it in this case.
So it's for rational homogeneity.
Rational homology. And what about the second one? Well, using Atiyah, Patodi and Singer Index Theorem for flat bundles. So how we do that? Well, so now it has to do with what Jean-Paul was talking yesterday about the Atiyah-Singer theorem. We have a closed Riemannian manifold, a vector bundle, self-adjoint elliptic operator. Since it's elliptic, the spectrum is discrete. Since it's self-adjoint, it has the spectrum is real. We can define this eta series, which converges when the real part of S is large enough. We can, with analytic continuation, extend it to a meromorphic map, which is finite at 0. The value at 0 is called the invariant. This doesn't take into account the 0 eigenvalues, so there's this modified series, which is takes into account H, which is the dimension of the kernel. And again, psi of A is just the value at 0. And this is a spectral invariant which measures the asymmetry of the spectrum in some sense. So now we take a representation and the corresponding vector bundle. Here, here should be a row, and here the small n, but sorry. We have the representation, the corresponding flat bundle. And one can couple the operator with this flat bundle. No? It goes from sections of the tensor product of our bundle with the flat bundle. And in general, this new operator, twisted operator, is not self-adjoint, but has self-adjoint symbol, and this is enough to define the series. So now we can compare, take the difference of the invariant of the twisted operator minus n times the invariant of the operator from twisted one, and here is the dimension of the representation. This is called the reduced psi invariant, and if taking module Z, this is a homotopy invariant of the operator. And well, we can, well, Atiyah, Patodi and Singer define an analytic index. It's the same setting. The homotopy class of the operator depends only on the homotopy class of the leading symbol. So we take the contingent bundle, and there is a bijection between stable classes of self-adjoint symbols on the manifold and K1 of the contingent bundle. If we fix the representation and we take the map, we take the operator to this with the reduced invariant, this gives the analytic index, not taking the class of the symbol to the reduced invariant. It's called the analytic index. There is also a topological index. The representation defines an element in K1, that should be K minus 1 of M with coefficients in C mod Z. There is a pairing in K theory and homomorphism from K0 of the contingent model 2, which extends the usual topological index. And we take the class of the symbol and send it to this homomorphism of the product of the class given by the representation and the symbol. This gives a number, which is the topological index. And of course, Atiyah, Patodi and Singer Index Theorem says that the analytic index and the topological index coincide.
So can you go one page back? So,
yeah.
So of course you go to T star M, but M, it could be any compact smooth manifold at the moment. We want nothing.
Yes.
And T star M is case theoretical oriented because, for example, it's a symplectic manifold, so it has an almost complex structure, and so that means you can get this homomorphism to degree 0.
Yes. So in the case the representation is unitary, then both indices are have values in our mod set. And in this case, the twisted operator it is self-adjoint. So our theorem is that if you take the manifold, the orient combat tree manifold, be the Dirac operator, this when we take the class of the symbol of the Dirac operator, and we take in this case a topological trivial representation. This is an important hypothesis. Then this second CCS number of the representation row is precisely the topological index. And my Atiyah, Patodi and Singer Index Theorem, but is equal to the analytic index. So one way to compute this second CCS number is just computing this invariant. So here is really
How did Dirac operator you need a spin structure?
yes.
And this is not dependent.
Well, every compact oriented tree manifold is true.
You're assuming it's a homology sphere?
No.
Because it may have many spin structures.
Well, yes.
Depends on the choice of the spin structure.
Yes. Yeah, but in this case, yes. Later, we will have just one, because it will be a homology.
Okay.
And well, of course, this is related with the question yesterday: what means spin singularity? So,
Yeah, but of course, it's a very different context, but I see the similarity we discussed yesterday. So even if the boundary is topologically trivial, because you are looking at the secondary invariants, and I think yesterday we discussed this relative obstruction. So even if the boundary is trivial, because you take a refined invariant, or even then the secondary is only working, it still carries information, even though the boundary is trivial.
Yes, yes. So the naive way to say the singularity is spin is, well, yesterday was mentioned, the regular part is spin, but maybe it's not enough. Or the link is spin, no? Or the question is, when is enough to have this or not to say something about the singularity? No?
Okay, so the game will be in the end, your oriented tree manifold will be the link of an isolated surface.
Exactly, that's the way I go. So now, for the case of a rational homology sphere, we have a formula when the representation is no longer topological trivial. It can be any representation, and now we have this corrected term, which is the reduced invariant of the determinant of the representation. So in this case, we have for any representation. So, well, so now I will change a bit of subject, but I think it will be related to something.
Just seeing this title. So before it was topological case.
Yes.
And the important point is, of course, which I'm realizing is you are working with odd degrees of topological case. So this is quite different from what we have done with these characteristic classes and before. So I think I said all degrees are even degrees.
No, yes. Now
you are leaving algebraic geometry because you go to links and these kind of things.
Exactly.
And this is really analysis or topological.
Exactly. But now we are going to algebraic theory. So, well, what we are going to do is, given a topologically trivial representation of the fundamental group of our oriented tree manifold, we are going to construct elements in the third algebraic theory group of complex numbers. And, well, so the first lemma is that the representation is topologically trivial if and only if it factorizes through SL and C. And then, well, this SL and C, well, with strict probability, well, it's perfect. I take the limit, taking the strict topology. This group is perfect. And
what do you mean by perfect?
It equals to its commutator.
What do you mean by limit? I mean, how do you divide this tree? It's not very hard to make choices like what you put like your border. This one, I guess you put like just the one, the diagonal, and just put 0, 0, 0, 0. Okay.
So, and well, the algebraic theory groups are just the homotopy groups of the Williams plus construction of the classifying space. So Williams plus construction, what it does is to the space, attaching 2 cells and 3 cells, you kill normal perfect subgroup of the fundamental group. In this case, is the whole fundamental group. but the homology stays the same. No? You don't change homology. So in this case, the Hurewicz of homomorphism is an isomorphism, and well, the definition of the homology of the group is just the homology of the classifying space, and since the homology of the classifying space is the same as the class construction, so we have this. And in this case also, we have a stability isomorphisms if n is bigger or equal than 3. And H3 of C is the same as just H3 of SL and C. So we have H3 of C is just this homology group. And then we have again our compact oriented manifold, take the topological trivial representation. We can compose with inclusion to this group. And we take the map of using homology and we push the fundamental class. This gives us a class in algebraic theory. So we denote it by L, the manifold, and draw the representation. Of course, if n is 3 or bigger, we don't need to compose with this inclusion because the homology of this SLNC is already C is algebraic theory as well. So when L is a rational homology sphere, we can extend this by using the trick we said before. Now this representation is topologically trivial, so we can take now this representation instead of rho to get an element in H or C.
So if you take the classifying space of SL, that's like a Grassmann bundle. So it should not have odd cohomology or homology. So you have H3 there. Maybe I'm missing something. Go to 2 slides ago. Yes, for example. This is a little bit. Yeah. So maybe one slide after when you put BS. Yeah. When you put. So when you put the classifying space H3 BS, so that's
H3 BS,
yes. So that's the classifying space of SL. So that's like a Grassmann bundle. So it should not have odd cohomology unless maybe.
Well, here, no, yes, because well, you don't put it here, but I'm taking discrete homology.
The discrete changes stuff.
Yes, and this is well, the classifying space is just the Allenberg-MacLane space, and then well, with the class construction, you just kill the fundamental group. Okay, so now, well, what is the relation with these classes and these CCS numbers? Well, we have our manifold, the representation, and well, since the topological trivial, so that means the image is in SL and C. We take the classifying map. Well, here is a more subtle because Cheeger and Simons use the universal bundle with connection because you need so. So well, I'm not giving here details, but here is the classifying map with connection, and here I'm thinking of this flat bundle with connection and seen as the pullback of this universal bundle with connection. And so also since Cheeger and Simons constructed some universal class, there is some class here in this group, such that our Cheeger-Chern-Simons class is just the pullback of that class in this group. And well, the second CCS number, evaluated in the fundamental class, is just the pullback of this class, evaluated here, which is the same as evaluating this class in this homology group in the image of the fundamental class. If n is bigger or equal than 3, this image is precisely the element in the theory that I just defined. So, so then evaluating this class in this element in the theory given by L and the representation gives me the second CCS number. And this, well, now I will go to the case of integral homology sphere. In this case, every representation is topologically trivial because it must have image in the special linear group because the fundamental group is perfect. And there is a construction by Jones and Westbury. In this case, the integral homology sphere. What they did is, well, you have the representation, you take the corresponding map into the classifying space, and you compose with the inclusion to the limit. And the plus construction is functorial, so you get a map between the William plus constructions. The plus construction of a integral homology sphere is the sphere, so you take the homotopy class of this map, it's an element in pi 3 of this plus construction of classifying space, which is an element in the theory. So our construction is, sorry, before, and they consider a regulator homomorphism, which is if you evaluate the class they constructed here, you get, well, the reduced psi invariant. Since the representation is topologically trivial, this corresponds to the second CCS number. And, well, what we did is a generalization of Westbury and Jones construction because, well, with these isomorphisms, no, the correct homomorphism, the inverse of the stability isomorphism, Jones and Westbury constructed the element here, we constructed our element here, and they coincide under this homomorphism to get the reduced psi invariant. So we extended for not only integral homology spheres, but for rational ones. Now.
So what was improvement? So you can work with
yes, we can work with rational homology spheres or compact three-manifold with trivial, topological trivial representation.
And you don't need this regulator.
No, well, what I'm saying is that the incarnation of this homomorphism you are seeing here in homologies rather than in homotopy.
I think these regulator maps are very difficult to control.
In general, yes. Yeah, they have formulas for when you have the integral homology sphere and you have explicit representation, they have formulas to compute the real part of this number. Okay, so singularities. So well, we have take a complex analytic normal surface germ. We take the resolution, it is always the exception divisor is denoted by E, and these are the reducible components. We will use the minimal resolution, which means that any other resolution factorizes through it. And when we have the group of divisors, the support of the divisor is the union of the curves. And the divisor is a cycle if the support is contained in E, and is rational if the coefficients are rational. It's effective if the coefficients are negative. There is an order in cycles, a notion of intersection of cycles, and there is one minimal element, the fundamental cycle, which satisfies this intersection inequality. And when the link, we take the link, and it's a differentiable manifold, which depends on, it's independent of the radius, if it's small enough. So it's an invariant of the singularity. And we have this following characterization of the fundamental groups of the links. If the fundamental group is finite, if the singularity is a quotient singularity, if it's infinite, then the link is an Eilenberg-Magdalena space of type K by 1 of L1 and is torsion free. And well, the geometric genus is the dimension of this group. The singularity is rational if the geometric genus is 0, and quotient surface singularities are rational normals. So, well, so we have a normal surface singularity, and we take the link, and we take homology class in H1 or the fundamental class of the link. So since the link is an invariant of the singularity, a priori these numbers can be thought as invariants of the singularity. So, but the question is, do they really say something about the singularity, or they just invariants of the link? Or the question is, when, in which cases they say something, or maybe in others they don't. So, well, so I would concentrate in quotient singularities, which is I mentioned. So, elements of GL to C are pseudo reflections if they have one as an eigenvalue. Group is small if it doesn't have any pseudo reflections. So quotient surface singularity is a germ of this type, C2 modulo the action of a small finite group of GL to C. Quotient singularities are equivalent if they are not isomorphic, and pre-prove that two quotient singularities are equivalent if the corresponding groups are conjugate. So, so the classification, well, any finite group of GL to C is conjugate to one of U2. So quotient surface singularities are classified by small finite subgroups of U2, and Briscoe gave the list of all these finite subgroups. We have a special case, which is Kleinian singularities. If we don't know, like this presentation of a group, all the finite subgroup of SU2 are small, and they are cyclic groups: binary dihedral, binary tetrahedral, binary octahedral, binary icosahedral. And these are the corresponding presentations. And this is a particular case of quotient surface singularities are called Kleinian singularities, or many names, Duval singularities, AB singularities. So I will concentrate on this. So the links of quotient singularities are spherical tree manifolds or spherical space forms. They are also rational homology tree spheres. That's why I focused on rational homology tree spheres before. And we have the corresponding CCS numbers. And for the case of these manifolds, the quotients of the spheres by finite subgroups of SU2, I gave formulas for these reduced sign invariants because I was working in this regulator map of Jones and Westbury, and I was trying to compute this. I was trying to compute it by the case when gamma is the binary icosahedral group, because in this case, this manifold is integral homology sphere. No? But I would compute it for any finite subgroup. And also, I said this generalized formulas by Pepe, he did it in the case of the twisted derived operator.
So here's the same question. Was the choice of the Dirac operator, or is here the unique structure?
In this case, is unique because in the case that I was interested in binary icosahedral group is because the fundamental group is perfect, so H1 is 0, so you don't have just one. So we have different surface quotient singularities whose links have the same fundamental group. So we have if we take a Kleinian singularity with cyclic fundamental group, the link is a length space. But we have all the quotient singularities which are not Kleinian singularities. We have length spaces as fundamental links, and so the fundamental group is cyclic. So sometimes we need to enrich these CS numbers with information coming from the singularity to say something about it. So I will show you an example of this. This is an application. So this is an invariant of hypersurface singularities called the spectrum, which is a multiset. So it means it's a set of numbers with multiplicities. There are mu of them, with mu is the Miller number. And this come from mixed fudge structures that I still don't understand. But the spectrum is an invariant of the singularity. If the two functions are right equivalent, then we have the same spectrum. They are contact equivalent as well. They have nice properties. One of them is we have a spectral number, then the exponential. This exponential. Then this is an eigenvalue of the homological nodal transformation. So in other words, the spectral numbers are specific logarithms of the monodromy eigenvalues.
Do you want to assume that F has isolated singularities?
Yeah, well, in my case, I will do the case of Kleinian singularity. So we have like it will be normal and surface it will be special. And well, the spectrum of these Kleinian singularities is known. There are these numbers. All of them have multiplicity 1 except this guy here has multiplicity 2. And well, as I said, we need to enrich this CS number. So what we do is, we can define this in general, no, for any normal surface singularity. Then I will concentrate on the Kleinian singularities. Agustin will talk later in more generality. We take a resolution, and we take the fundamental cycle. No? We have here the coefficients of the fundamental cycle. And what we do is this second CCS number, we take this factor, which is with this multiple, which is given in terms of the coefficients of the fundamental cycle. And well, this number depends on the resolution. And our theorem is that we have a diagram of a Kleinian singularity. We don't know, as before, by L the link. The spectrum as its multiplicities can be obtained from the non-zero first CCS numbers of the reducible representations of the fundamental group of the link, and appropriate multiples of this new invariant I just defined, where the representation is within a natural representation into S and C, and I will take the minimal resolution. So, how does this work?
What do you mean by network? What do you mean by the network representation?
Yeah, because the Kleinian singularities are quotient singularities. You have finite subgroup of GL to C.
Yeah, you add by this group on C.
Exactly. So these are subgroups of SL to C, or even of SU. No, you can make them conjugate to subgroups of SU.
Can you go back one slide?
Yeah.
So what is the reason for the strange factor in one slide like this?
Well, the first reason is because this one is the multiplicity works, you will see. But there are many questions there. So I will finish with questions in the spirit of this meeting. But yes, the reason is the one we put. So we have two cases. One when the group is cyclic and non-cyclic. In the case of when it's cyclic, all the different non-zero first CCS numbers of irreducible representations with respect to the generator are the spectral numbers with multiplicity 1. In the non-cyclic case, we need to take the first CCS numbers, the non-zero CCS numbers, with respect to this class. With this class, remember, I listed the finite subgroup of FC2 and gave a representation of the group which has two generators, B and C. This is the image of the generator C in the Abelianization, which is H1. And all of them, all the non-zero first CCS numbers are spectral numbers with multiplicity 1. And this CCS number can appear the same number several times, but you just take them once, just multiplicity 1, even though they appear several times. And this number, when it's not zero, this capital psi is of the form 1 over m for some integer m. This will be a spectral number with multiplicity 1. And the rest of the spectral numbers, we have, again, two cases. In the case of binary dihedral groups, we take all the odd multiples of this number from odd multiples with I running from 1 to R, and also with multiplicity 1. For the binary polyhedral groups, we take the multiples which are co-prime with M, with the denominator of this number. Also with multiplicity 1. So let's see. So in the case of this, I take the fundamental class, and I will denote by this multiple I defined. So in this case, this number is 1, but the second numbers are 0, so this is 0. So the spectrum consists only on first CCS numbers, and all of them are different, and this gives precisely the spectrum. This is the most interesting case because binary the hydra group is even. Here we have the first numbers. We have to take it with respect to the class C bar. Here we have 1/2. So this 1/2 is a spectral number. Here we put the spectral number. So here is the spectral number. And then I take row 1 is the natural representation. This is the second CCS number. This is the factor. So we'll get 1/2 times r plus 1. No, this is a spectral number, and I need to take all the odd multiples. Okay, you see here the next odd multiple is 12 plus 1, but 12 plus 1 is r plus 1. So r plus 1 cancels with this r plus 1, and you get 1/2. So here is this why this 1/2 has multiplicity 2, one coming from the first CCS number, and the other one as a multiple of this number. In the odd case, this doesn't happen. Again, we have 1/2, but since I take the odd multiples, and this number is odd, then I won't get 1/2. So this just have the odd multiples, and 1/2 in this case will have multiplicity 1. And the others, well, are analogous. You take the first CCS numbers, so here 1/3 is for 12, 2/3 is 1. 1/24 is, well, the alpha 4 is the natural representation. This multiple is 2, so we have 1/12. This is a spectral number, and we take all the multiples which are coprime with 12. This is the same, analogous. You have this one, and well, we have all the multiples which are coprime. In the case of binary cosahedral, we don't have first CCS numbers, so all the spectral numbers are just multiples of this one. And so if we got it like this, this is sort of analogous to Mackay correspondence, that you have this, you get this. Question, why?
Yeah, so this is just Babut calculation.
Yeah, so quoting Arnold, much progress in singularity theory is based on empirical data. Some of these empirical data later become theorems. We hope to get one theorem from here to explain why from these CCS numbers you get the spectrum of which. And